Okay, fantastic. So, a brief initially, what are the different topics we are going to study? What are different topics that you different subjects we are going to study, in fact? Okay, so we are going to have 5 classes. We'll have 5 classes, right? So, what are the 5 classes? Class 1, let us have a quick overview, right? In class 1, we'll go through simple mechanisms. Okay, so this is the most important chapter, I will say. Okay, lot of theoretical questions are being asked from this chapter, right? Then class 2 will be of velocity and acceleration analysis. Velocity and acceleration analysis, right? Then class 3 will be for gears. Class 4 will be for flywheel and governors. Then class 5, last class 5 will be for the remaining chapters. Those are balancing. You have gyroscope, because these are very small topics. Cams and folders. Camps and folders, right? So this is how it is going to be, right? And in between somewhere here, okay, we'll find out some time, right? So velocity and acceleration analysis might not take complete one class. So in that case, what we'll do, we'll start gears at the second class, and third class after gears, we'll try to do a little bit of dynamic analysis of slider crank mechanism. Dynamic analysis of single slider crank mechanism. Okay, so all of you ready to start? Yes, gears will be different from that of machine design. Okay, it will be completely different. Okay, it will be completely different from that of machine design. So here you will see with the mechanism point of view in machine design. Better not to say machine design, it is design of machine elements, DME. So in DME, we'll see it in design point of view. How exactly you are going to design a gear. Here we are going to see with the point of view of mechanism point of view, right? How does gear function, right? How does two gears mass? How does the gears function? And their terminologies of many other things. Okay. Okay. So are you ready to go? Give me a yes. Fantastic, right? So start with simple mechanisms. Simple mechanisms is, I'll say, the most important chapter, right, of all. Lot of questions can be formed from here. Lot of questions can be formed, small 1 mark question, right? And mostly this chapter is theoretical in nature. Very less numericals will be there, hardly 1 or 2. Few numericals will be there. That also we are going to discuss, right? Let us start with simple mechanisms. Okay, so yes, we'll be fast. Okay, we have to go fast. Lot of things are there. You can see there are 27 slides here. There are 27 slides here, right? So we have to go fast. Okay, we have to go fast. So okay, so let us start with a kinematic link or element. So what is a kinematic link or element? I'll not be able to explain it in very detail, okay, but I'll go through so that whatever questions are there, you should be able to attempt those questions. You should be able to mark those questions correctly, right? So this is the smallest element. Okay, the smallest kinematic link or element, you can say the smallest part of a mechanism. Okay, so what exactly is a mechanism? By the way, what exactly is a mechanism? right? Any machine will have a mechanism inside it. Any machine will have a mechanism inside it. For example, if you uh, see a vehicle, right? If you see a automobile, right? If you take any automobile you want, if you take an automobile, right? You get to see the outer structure of the automobile, right? You get to see the outer structure of the automobile, but inside there are lot many mechanisms, right? You have the IC engine, that is nothing else but mechanism, right? Machine, that is a machine, but the machine runs on a mechanism. That is what we are going to see in this chapter. That is what exactly we are going to see in this chapter, right? So you have the steering mechanism, right? You have the braking mechanism, you have the transmission mechanism, all different parts of inside the vehicle is are different mechanisms, right? What you get to see is the overall structure, but inside it is made up of many different mechanisms, right? So if you consider any mechanism, be it the steering mechanism, be it the transmission mechanism, be it the braking mechanism, be it a gearing mechanism, whatever mechanism you consider, the smallest rigid part, the smallest part of the mechanism is known as kinematic link or element, right? So links can be rigid, it can be flexible, it can be fluid link, right? Rigid like connecting rod, this is an example of a rigid link, right? Belts are example of flexible link, right? Similarly, we can also use fluid. We can also use fluid, like you can use nitrogen. Generally, nitrogen is used for pneumatic devices, right? Air is also used, okay? Or we can use any hydraulic fluid. Any hydraulic fluid for your hydraulic devices. These are also used to transmit power, so they can also be considered a part of link. Okay, so now this is important. This is important. Okay, this is something basic. This is something basic. Types of relative motion. Types of relative motion. Right. So there can be the relative motion can be classified into three types: completely constrained, successfully constrained, and incompletely constrained. Completely constrained, successfully constrained, and incomplete constrained. Let us try to understand each and every one. Right. So if I say complete constraint, completely constrained, right? What it means, motion is possible only in one direction, irrespective of the direction of force. It does not matter in which direction you are applying the force, right? You might apply the force in this direction, you may apply the force in this direction, whatever direction you want to apply the force, it does not matter. If motion of the element has to take place, there is only one possible direction of the motion, that is towards left or towards right. Can you see this? What is this? This is a rectangular bar inside a rectangular slot, right? The rectangular bar inside a rectangular slot. You can see rectangular slot, right? So this kind of motion is known as constrained motion, where there is only one direction of motion possible. Motion is possible only in one direction, irrespective of the direction of force. You might apply the force in any direction you want, but the motion is possible only in one direction. The next is successfully constrained motion. Successfully constrained motion. What is successfully constrained motion? Right? It is a motion where motion is possible in more than one direction. Is possible in more than one direction, but made to happen only in the direction by some external means. But made to happen only in one direction by some external means. Let us take an example very quickly. Okay. Can you see this cylinder? Inside the cylinder, there is a piston. Inside the cylinder, you can see there is a piston. Right? So now the piston, what are the types of motion the piston can do? Right? Just initially forget the connecting rod. Just forget that there is no connecting rod, there is no crank, nothing. Right? The piston, simply the piston inside the cylinder. Simply the piston inside the cylinder. So what kind of motion the piston can do inside the cylinder? There are two types of motion the piston can do inside the cylinder. What are those? One is the to and fro motion. The piston can make some to and fro motion inside the cylinder. It can go inside the cylinder, it can come out of the cylinder. That is one kind of motion. What is the other motion that is possible? Can you think about it? What is the other motion The other motion is the rotation. Yes, the piston, cylinder, they're circular. What cross section do they have? Generally, they will have a circular cross section. What kind of generally, right? It's not necessary, but generally 90%, more than 90% of the cases, they will have circular cross section. Circular cross section. So if there's circular cross section, the piston can rotate inside the cylinder, yes or no? Definitely yes. The piston can rotate inside the cylinder. So that is the second motion possible. So motion is possible in more than one direction. But now if you connect the connecting rod, my dear friends, now if you connect the connecting rod and then fix it to the crank and then fix it, now tell me how many motions are possible. Now tell me how many motions are possible. There is now only one motion possible. Which one? That is the to and fro motion. That is the to and fro motion. The rotation of the piston is now prevented. The rotation of the piston is now prevented because it is not joined to the connecting rod, right? So this kind of motion are known as successfully constrained motion. So you have successfully constrained it. You have successfully constrained it. The third kind of relative motion is incomplete constrained motion. The third kind of relative motion is incomplete constrained motion. So motion is possible in more than, so here the motion is possible in more than one direction, right? And is dependent on the direction of force, the type of force you are applying. For example, you can see here, I've given you an example. What is the example? A round bar, round in the sense a bar of circular cross section, a bar of circular cross section inside a circular hole, right? So you can see here, it depends. The motion depends on the kind of force you're applying. There can be a to and fro motion. At the same time, there can be a rotational motion. There can be to and fro motion and there can be a rotational motion, right? So which kind of motion? Which kind of motion? So these are the three types of relative motions possible. So there is a question, give me the answer fast. These are the three types of relative motion: completely constrained, successfully constrained, and incomplete constrained motion. Yes, what would be the answer? I'm just giving you, see, I'll not go through each and questions, I'll not give you questions from each and every concept, but I'm showing it to you initially. I'm showing it to you initially that whatever we are going to learn, in today's class, each and everything is very, very important, and each and everything can have many different questions framed, right? Square hole means square bar in a square hole means this is a square hole. Okay, inside this there is a square bar. I know थोड़ा सा fast है, but there is no other way. ठीक है, I'm trying to cover maximum. This is a square hole and inside that there is a square bar. Yes, it is a completely constrained, right? So similar to this, basically it is the same example. Okay, basically this is the same example we are talking about. The same example we are talking about, right? Here it is a rectangular bar in a rectangular hole, right? Only motion is possible only in one direction, right? So it is, what would be the answer? The answer is it is completely constrained motion. The answer is completely constrained motion, right? So in machine, what kind of motion do you want? A simple question to you. In machines, what kind of motion do you want? Which one of the three relative motion ठीक है, it might be one or more than one. Would you prefer all three? Would you prefer two? If this two, which two? Or would you prefer a single one? Which motion do you think will be the best for any machine? Come on, we don't have the privilege of time. No, we'll not go for all. We will not look for incomplete constrained motion. For example, I'll just give you an example. In any machine, once you put in the input, you want a desired output. Desired output, right? If you put the input, you want a desired output, right? So this desired output is very, very important. For example, I'll give you a simple example. When you drive a car, you put your vehicle on the first gear, right? Then you press the accelerator, slowly remove the clutch. What do you want? Your vehicle should move in the forward direction, or there should be a doubt. Sometimes it will move forward, sometimes it will be moving backward. Which would you prefer? The first one or second one? You got into a car, you're going for office, suppose. You got into a car, you started the car, right? Then you put the car on the first gear, you slowly remove the clutch, slowly press the accelerator, right? And the car starts moving. In which direction do you want the car to move? Forward, backward? Forward, right? What if there was some confusion? Sometimes the car would move forward, sometimes the car would move backward, dependent on all the environmental condition, right? That is not a desired output, right? That is not a desired output. So that is why we don't want any incomplete constrained motion in our mechanisms. If there are incomplete constrained motions in our mechanisms, that might result in undesired results, right? You want to do something, but the what is being produced, what is being delivered is something else. The result is something else. The output is something else, right? So that is not something which we want in machines, right? So the only two, the first two, that is completely constrained motion, because motion is possible only in one direction. So if you use this kind of machine mechanisms, the mechanisms in which motion is possible only in one direction, right? Then definitely you are going to have a desired output. Similarly, successfully constrained motion will also do. Initially it was not constrained, initially it was incomplete constraint, but by means of um, some way we have converted into constrained motion. So we want only, this is what we want, this or this. What we want. Okay, so always remember, either completely constrained or successfully constrained. We don't want incomplete constraint. Okay, now we got to know what is a link, right? It is a minimum you can say the smallest part of the mechanism, right? Now if we join two links, we are going to have a pair. Okay, if we join two links, we are going to have a pair, and it is not necessary that they be joined to each other. Okay, they be joined to each other. Any two links which have relative motion to with each other, any two links which have relative motion with each other will be called as a pair, right? I'll give you an example. Suppose there are three links. ठीक है, अभी बहुत सारे एग्जांपल देखने वाले हैं, एक, दो, तीन, चार, पांच, ठीक है, all are having relative motion with along with each other, ठीक है. So 1 2 3 4 5. So how many pairs will be there? 1 and 2 will also form a pair, 1 and 3 will also form a pair, 1 and 4 will also form a pair, 1 and 5 will also form a pair. So if there is any relative motion, okay, it will definitely form a pair, right? Now suppose let me say, suppose the link 1 is fixed, I fixed link 1, and link 5 is fixed. Please try to understand very carefully. You have to cover a lot many things in a very short period of time, right? So initially we have seen that 1 2 will form a link, 1 3 will form a link, 1 4 will form a link, 1 5 will form a link, right? Okay, now suppose in the new system, what you have done, we have fixed linked one somehow we have fixed linked one. Similarly, you have fixed linked 5. Now 1 and 5 will not form 1 and 5 will not form a pair, not a pair. Why? Both of them are fixed. Both of them are fixed. If both of them are fixed, what is going to happen? Both of them are fixed. What is going to happen? There is no relative motion between them. And if there is no relative motion between them, then it is not going to be a pair. Okay. So we'll develop this concept in future, whatever slides we are going to have. Okay. Now, all the motions that we are talking about, all the relative motions we are talking about should be constrained, either complete constraint or successfully constrained. Okay. Let us see some different kinematic pairs available for us, right? According to the relative motion, the first one is the turning pair, pin joint, hinge joint, or revolute joint, right? We represent it something like this. There's link 1 and link 2. There's link 1 and link 2. I'll give you an idea. Very simple idea I'll give you, right? Have you seen scissors? Have you seen scissors? Do you have scissors at your home? Do you have scissors at your home? Yes. Have you seen scissors? Means you have seen scissors, right? So have you seen the joint where the two parts of the scissors are fixed to each other, joined each other, right? There are two parts. Generally, scissors, we have two parts, right? Both of them are hinged. Both of them are joined in the middle, right? That where it is joined is nothing else, but it is the revolute pair. We also call it hinge joint, pin joint, turning joint. We have many other examples. We can go through it, right? I hope you have understood what exactly do I mean by a turning pair, right? I hope you got what do I mean by turning pair. Okay, so there will be two links in a turning pair. Okay, there will be two links in a turning pair of pin joint. Okay, the next is the sliding joint. Okay, sliding pairs or prismatic pair. We have two names: sliding pair or prismatic pair. So if a member is sliding on another member, if a member, this say link 1, and this is link 2, the fixed link is the link 2, let me say the fixed link, or it might not be fixed, whatever, it might be fixed, it might not be fixed, right? So this is nothing else but the sliding pair. This is nothing else but the sliding pair, right? So this is sliding over surface, right? So whatever we are saying, 1, 2, what are these? These are links. What are these? These are links. What is a link? What is a link? It is the smallest part of a mechanism, we can say. It is the smallest part of a mechanism, right? It is the smallest part of a mechanism. Link. Okay. What next? You have rolling pair. You have rolling pair. If something is rolling on some surface, this is 1, this is 2. Then if a screw pair, right? You have a screw. So what is the speciality about screw? It has both it at the same time it will also rotate and it will also move downwards. So rotation and sliding simultaneously. Rotation and sliding simultaneously. Rotation and sliding simultaneously. Okay, so what is a spherical pair? It looks something like that. Joystick of video game, look like something like this. Joystick of a video game, right? So there is a ball. There is a ball inside, right? It can rotate in all the directions. It can rotate in all the directions. It can rotate in all the directions, right? We can give the example of our wrist. Rolling spherical pair. We can give example of a wrist. Wrist is an example of a spherical pair. You can say the wrist is example of a spherical pair, right? So we have generally three joints. Okay, so we have generally three joints. Okay, in our body, in our hand, you can say. Suppose this is the body. Then you have the arm. Sorry, shoulders. Then you have the arm. Then you have the wrist. Right now, the perfect of the all the drawings. Okay, so there are three joints. Here you have one joint. Here you have one joint. Here you have one joint. Right, 1, 2, 3. Can you tell me if all of them are spherical pairs? Yes or no? All of them are spherical, or do you have some other opinion? Let me see. Can you feel your arm? Can you feel your hand? Your hand will have three joints. I'm not talking about the fingers, but if your hand at the wrist, then you have something. Yes, very nice, Naveen. 2 is a turning pair. 2 is a turning pair. The joint connecting your arm and your shoulders is basically a turning pair, right? This is basically a turning pair. And what about your shoulder joint? What about 3? Shoulder joint. What do you think about your shoulder joint? It is a spherical pair. Your shoulder joint is a spherical pair, right? So there are many practical examples available, right? Some other time, if time permits, we will see. Okay. Now, according to type of contact, again, this is something important. According to the type of contact, there can be lower pair or higher pair or wrapping pair, right? So, lower pair, what does it mean? It means surface contact. Higher pair, it means point or line contact, right? Wrapping pair, it means when one link is wrapped over the other pair, right? When one pair is wrapped over the other pair, for example, belt pulley. Belt and pulley. Okay, देखते हैं. So what is lower pair? Lower pairs are those pairs which have surface contact, right? And what is higher pair? Higher pairs are those pairs which have point or line contact. Okay, so let us try to classify here. Tell me first, what kind of pair is this one? First one, turning pair. Is it a lower pair or higher pair? Turning pair is a lower pair or higher pair? What do you think? It will have surface contact. It will have surface contact. Okay, it's not a point contact, it is a surface contact, right? So because you see the joint will be not that very small. If you see this joint, okay, this is a small diagram I had made. Okay, if you see the joint, there will be good overlap. There will be good overlap at the joint. There will be good overlap at the joint, right? The two parts, they will have a good overlap. The surfaces of the two parts, right? Two links, link 1 and link 2, we can say surfaces of the link 1 and link 2 will meet each other. So this is basically an example of lower pair, right? This is example of a lower pair. What about this sliding pair? Is it a lower pair or higher pair? Clearly you can see there is a surface contact, right? Clearly you can see there is a surface contact. What kind of pair it is? It is a lower pair, right? If you see our rolling pair, what kind of contact is there? There's a line. If it is a sphere, for sphere it will be a point contact. If it is a cylinder, it will be a line contact, right? So basically rolling pair is example of a higher pair. Okay, screw pair, again it is a lower pair. Spherical pair, it is again a lower pair. Spherical pair, again it is a lower pair, right? So you might have to classify this. Sometimes small 1 mark questions are being asked. Okay, small 1 mark questions are being asked. Okay. So let us now go on to different types of joints. What are different types of joints? Binary joint. What do we mean by binary joint? Bi means two. If two links are meeting at a joint, it is known as binary joint. Ternary joint, if three links are meeting at a joint, then it is known as ternary joint. Quaternary joint, if four links are meeting at a joint, it is known as quaternary joint. Right? It is point to be noted here. One ternary joint is equivalent to two binary joints. This is something you will have to remember. One quaternary joint is equivalent to three number of binary joint. One quaternary joint is equivalent to three number of binary joint. Okay, so this is important with respect to degree of freedom. This is important. Okay, when you will find out degree of freedom. Concept is required to find degree of freedom. This is what we are going to see. This concept is required to find degree of freedom. Okay, so what we are talking about here is joints. Remember, what is this? Joints, right? This is a joint, right? This is a joint. This is a joint, right? This is a joint, right? Now, if I talk about links, I can also talk about links. Links can also be classified like that, right? Binary link. What is a binary link? If the link has two connection points, means you can join two other links to that link. It is known as binary link. Two ternary link. What is a ternary link? It will look something like this, or any link where you can join three other links. Any link where you can join three other links, it is known as ternary link, right? And you can have quaternary link. So what is a quaternary link? Any link where you can join four other links. Any link where you can join four other links is known as quaternary link. Okay, just have the know the difference. Here we are talking about links. Here we are talking about links, the smallest element, right? It could be binary where you can join two other links. It could be ternary where you can join three other links, or it could be quaternary where you can join four other links. Okay, here we are talking about joints. Here we are talking about joints. What are joints? Joints and links. You must be knowing the difference. What is the difference between joint and a link? Okay. So if you find I'm going fast anywhere, if you find you're not being able to follow whatever, right, you can please comment me on the chat box so that I will accordingly. Oh, okay, good, fantastic. Because you have lot of things to cover. Kinematic chain, right? We have seen link, that is smallest element. Then you have seen pair, that is two, right? Then similarly, if you go on, right, joining one link after the other, if you go on joining one link after the other, if you go on joining one link after the other, right, if you go on joining one link after the other, and make sure that all the relative motion are constrained, and finally you close the chain. Finally the chain gets closed in some way other. Finally the chain gets closed in some way or other, right? Close means the first link is connected to the last link. 1 2 3 4 5 6 7 8. The first link is connected to the last link, right? So in this case, if all the motions are constrained, all the relative motions are constrained, then this chain is known as kinematic chain. This chain is known as kinematic chain, right? This chain is known as kinematic chain. So okay, I'll tell you how exactly you get a mechanism. First of all, you will make a kinematic chain. kinematic chain. So you cannot use the chain unless and until you fix one of the link. You have to fix one of the link. One link is fixed. If you fix one of the links, what you'll obtain is a mechanism. What you'll obtain is a mechanism. What you'll obtain is a mechanism, right? To use the link. What I mean to say, if you want to use this link, you cannot use this link anyhow. You have to fix one of the links. Only then you will be able to use this chain. Sorry, you have to fix one of the links. Only then you will be able to use this chain, right? So if you fix one of the links, what you'll obtain is a mechanism, and if you put the mechanism to use, if you put the mechanism to use, what you're going to obtain is a machine. What you're going to obtain is a machine. Yes, the chain in bikes can also be said. Okay, this is just an overall example I am giving you. Okay, the chain, that is also chain, but for the chain to be a kinematic chain, all the motions should be constrained. That is something what you have to. Okay, I didn't see your chat. Sorry. All the motions has to be constrained in nature. Okay. So how to ensure if all the motions are constrained or not, that is what we are going to see in future. ठीक है, अभी हम देखने वाले हैं, वही चीज हम स्टडी कर रहे हैं, slowly evolving. We are slowly evolving. ठीक है. So a kinematic chain, you fix one link, you'll obtain a mechanism, you put the mechanism to use, you'll get a machine. You'll get a machine. Okay. Now, a very important point to see if a mechanism, how to use a mechanism, is finding the degree of freedom. So what is the degree of freedom? Is the minimum number of independent variables required to define the position and motion of a mechanism. Required to determine the position and motion of a mechanism. So why we are worried about position and motion of a mechanism? What is so important about position and motion? Because it is very important. For example, okay, again, let me tell you, okay, it is very important to know how much accelerator you press and what would be the speed of the vehicle, right? There should be a very definite relationship, right? There should be a very definite relationship. If you're riding a bike or you're riding a car, right, there should be a very definite relationship how much accelerator you are pressing and what is the speed of the vehicle. Similarly, even if you're riding a bicycle, how fast you're moving the pedal and how fast is the bicycle moving, there should be a very definite relationship, right? There should be a very definite relationship. So that is why we are very, very concerned about the motion. Right? All the mechanisms, right? We must definitely know the motion of each and every part. All the mechanisms, we must definitely know the motion of each and every part. So what about, just hold on. Okay. So what about position? The position and motion are all interrelated, right? Position and motion are all interrelated. If you know the position of a object, you can determine its motion, or vice versa. If you know the motion, you can determine the position, right? So what we want is, how many independent variables do you need to know to determine the position and motion of a mechanism? Not just position or motion of a mechanism, position and motion of each and every link of a mechanism, right? How many variables should I give you? How much of data should I give you? It's something like this. I'm giving you a question. I'm giving you a numerical question. What is the minimum number of data should I give you so that you'll be able to solve the question? I'm giving you a numerical question. What is the minimum number of data I give you, right? So that you can come out with the answer. Similarly, what is the number of independent variables should I give for a particular mechanism so that you are able to determine, you are able to analyze the whole mechanism. The analyze means kinematically and dynamically. Kinematically and dynamically analyze the whole mechanism. What are the different position? What are the different motion? If you know the motion and position, you can also find out the forces, and you can keep on going like that. Right? So let us first find out. Let us quickly see how many motions for three-dimensional mechanism is possible. So we have three axes, X, Y, and Z. Right? Let me say we have a cubical object. Let me say this is a cubical object. You can see, right? How many motions are possible? There can be motion in X direction. There can be motion in Y direction. There can be motion in Z direction. Right? Plus, there can be rotation, linear motion in X, linear motion in Y, linear motion in Z. Then you can have, then what you can have is rotational motion about x-axis, rotational motion about y-axis, and rotational motion about z-axis. So in total for three-dimensional mechanism, maximum degree of freedom is 6. Right? It's not like in your production, right? If you study production, you consider plus x and minus x as two different variables. You consider plus x and minus x, plus y minus y, plus z minus z as two different variables. So in that case, clockwise and anti-clockwise as two different variables. So in that case, you will have, if you have studied in production engineering, there are 12 degree of freedoms, but in Curio machines, the maximum degree of freedom possible is 6. So if I give you all the 6, you will definitely be able to determine all the motions. Okay. Okay. So what for two-dimensional mechanisms? For two-dimensional mechanisms, again X, Y, Z. It means that Z will not be there, definitely. Z will not be there. Okay, na? So X and Y. Right? Let me take up a square element. So for the square element, what are the different motions possible? There is a motion possible in X direction, motion possible in Y direction, and rotation is possible in the XY plane. So maximum degree of freedom here, what will be the degree of freedom maximum? Maximum degree of freedom is, the maximum degree of freedom is 3. Okay, so this is what we are more interested about. We are more interested about this because our syllabus is pertaining to only two-dimensional mechanisms. That is, no, it will not be 4, right? You might have thought of some other rotation. Linear in X and Y, right? Linear in X and Y. So 1, 2, and rotation in XY plane 3. Linear in X and Y and rotation in XY plane, that is 3. Okay, so this is what we are concerned about because our syllabus mentions planar mechanisms. Or simple mechanisms. It is also called simple mechanisms. Planar mechanisms or simple mechanisms, right? So for us, maximum degree of freedom will be 3, right? So now there was a scientist whose name was Kurzweil. He did very much of research onto these mechanisms, and he came out with a formula to find out what is the degree of freedom of a mechanism. He gave a formula to what is the degree of freedom of a mechanism, where F is nothing else but degree of freedom, L is number of links, J is number of binary joins, कौन सा join? Binary joins, and H is number of higher pairs. Number of higher pairs. H is number of higher pairs. Okay, so you have to remember this formula. Is a very, very important formula. Very, 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 very important formula. Lot many times questions are being asked from this formula. You left questions many a times from this formula. F is equal to 3L minus 1 minus 2J minus H. F is equal to 3L minus 1 minus 2J minus H. F is equal to 3L minus 1 minus 2J minus H. F is equal to 3L minus 1 minus 2J minus H. Okay. Now, we'll do a question. One question that is good enough. Okay. One good question we'll do. We'll not do simple questions. One good question we'll do. Okay. One good question we'll do. Okay. एक smaller question आप देख लीजिए. Time है. Time थोड़ा सा कम शायद हो जाए. ठीक है. Okay. One good question we'll do. ठीक है. Okay. Now, after Kurzweil, see, after Kurzweil, Kurzweil gave this equation, which is known as Kurzweil equation, right? So this equation was used, but it was not very convenient. Okay? It was not very convenient. Means people are not being able to understand how to use this equation, right? They were using this equation. They were using this equation quite a lot, right? But they're still finding some difficulties, right? They're unable to understand. Now there is another scientist whose name was Grubler. Okay, so what he did, he picked up his equation, Kurzweil equation. So he picked up the Kurzweil equation, okay, and he started doing research on this equation, 3L minus 1 minus 2J minus H. So this is the Kurzweil equation. This is the original Kurzweil equation, right? And the scientist named Grubler, okay, what he did, he started researching on this equation, and what he did, right? Okay, for example, right? He said that all the mechanisms, okay, all the whatever the mechanisms we are looking for in this chapter, right? This pertaining to this chapter, right? We want single degree of freedom. He said we want single degree of freedom. Why? We want single degree of freedom. I'll give you some example. Okay, degree of freedom. Okay, what is degree of freedom, right? Okay, fine. So as I tell you, I gave you an example. Okay, if I'm giving you a question, the minimum number of data, the minimum data should I give it to you so that you get the answer, right? So that is nothing else. You can correlate with degree of freedom. Now, please try to understand my point. Please try to understand my point because I also have to explain it to you in a very short time. Okay. Otherwise, I have the leverage of using 5 hours for this lecture. I'm condensing this in less than half. Okay. So definitely, it is also a challenge for me to make you explain everything to all of you. But still, I'm giving my try. So please try to understand all of you. Now, what exactly is degree of freedom? Degree of freedom is the number of inputs you need to provide, right, to get a desired output. How many input you need to provide to get a desired output? Let us do a small problem. क्योंकि एक problem से solve हो जाएगा, right? एक दो problem कर लेते हैं. Let us try to find out. Let me say this is a link. This is the mechanism. This is a link. ठीक है? This is the mechanism. I know. Thank you for all the support, Naveen. Okay, thank you for all the support, Naveen. Okay, let me say this is the mechanism. So what do I have in this mechanism is there are 4 turning pairs, you can see, right? There are 4 turning pairs. There are 4 turning pairs, right? And there are 4 links. There are 4 links. What are the 4 links? Can you say? This is link number 1, this is link 2, this is link 3, this is link 4. So how many links are there? If I say L is equal to 4. L is equal to 4. How many binary pairs are there? Can you give me the number of binary pairs, binary joins? Can I say the number of binary joins? That this is one binary join, this is one binary join, this is one binary join, this is one binary join. I'm considering the turning pairs as the binary joins, right? So number of binary joins is also 4. Can you see this? Number of binary joins is also 4, right? Can you find any higher pairs here? There are no higher pairs. As you can see, there are no higher pairs, right? So here, if I want to find out the degree of freedom, what is the degree of freedom? Degree of freedom is equal to 3 times, right? 4 minus 1 minus 2 times 4 minus 0. That is 3 is a 9, 9 minus 8 is 1. So basically, degree of freedom here is So what does this mean? What does this mean? Degree of freedom, if I'm finding it out to be 1, what does it mean, right? Degree of freedom, I'm giving you another definition of degree of freedom. You can say I'm giving you another definition for degree of freedom, right? Degree of freedom. I'm giving you another definition of degree of freedom. It is the number of inputs required to obtain a desired output. The number of inputs required to obtain a desired output. Okay, so this definition is same as that of what we have studied. Here the definition, whatever this definition we are talking about, whatever this definition is talking about is very simple, right? It is very, very similar to that of what we have already gone through once. Earlier, what you have said is the number of independent variables to define the position and motion. Position and motion I have said as output. What is position and motion? I am saying position and motion as nothing else but output, and number of variables I am saying as input. Right? Number of variables I am saying as input, and the position and motion I am saying as output. Right? So how many inputs you require to obtain a desired output? So in this case, we require one input. Right? In this case, we require one input to get a desired output. Right? For example, to use this mechanism, you have to fix one of the link. You have to fix one of the link. Now, without fixing, ये तो हवा में रहेगा. This link will be in air. How can you use this link? How can you use this mechanism? It will be in air. You will not be able to use it, right? So you have to ground it first. So to ground it, you have to fix one of the link. So after fixing, right? After fixing, suppose this is the input link, then here you'll get the output. This is the input and this is the output. So how many input you are giving to get a one output? One input for one output, right? One input, right? So this is possible only when degree of freedom is equal to 1. Degree of freedom is equal to 1. This is possible only when degree of freedom is equal to. What will happen if degree of freedom is 2? Let us take an example. जल्दी जल्दी आप ही बताइए, ठीक है? All of you try to solve this question. All of you try to solve this question. Try to give me the degree of freedom fast. Try to give me a degree of freedom. You have 30 seconds in your hand. You have 30 seconds in your hand. Give me the degree of freedom. How many links are there? 1, 2, 3, 4, 5. Always start from the fixed link. Always start from the fixed link. The fixed link, you number it as 1. How many binary joint? All the joints you can see are turning pairs. All the joints you can see they are turning pairs. 1, 2, 3, 4, 5. So 5 binary joint. Can you see any higher pair here? No higher pair. So degree of freedom F is equal to, very nice, Naveen, right? 3 times 5 minus 1 minus 2 into 5 minus 0. That is 4 3 is 12 minus 10 is equal to 2. So here you can see the degree of freedom is 2. See, degree of freedom 2. So what does it mean? It means that two inputs. What does it mean? It means that two inputs are required to obtain a desired output. Two inputs are required to obtain a desired output. For example, if you see this link, right? If I talk about two inputs, right? If I talk about two inputs, you have to give two inputs. आपको क्या देना पड़ेगा? You have to give two inputs. input 1, input 2. Only then you are going to get a desired output. If you give two inputs, okay, if you give two inputs, input 1 and input 2, okay, then you'll get a desired output, right? So generally what we want is we want single degree of freedom, because it makes our life convenient. Only one input, one input, one output, one input, one output, right? So this is what we are looking for. At least this is what you are looking for. So most of the mechanisms will have single degree of freedom. Most of the mechanisms will have single degree of freedom. This is what we are looking for, right? So if most of the mechanisms have single degree of freedom, and you have seen, and most of the mechanisms will have no higher pair. Most of the mechanism will have no higher pair. Most of the mechanism will have no higher pair. No higher pair means h is equal to 0. Most of the mechanisms will have single degree of freedom and no higher pair, right? So in the Kurzbach equation, what did Grubler do? He substituted f is equal to 1 and h is equal to 0. He substituted f is equal to 1 and h is equal to 0. So, and then he came up with an expression, okay, of this kind. Then he came up with an expression. We can solve it. Okay, we can solve it. You just need to substitute f is equal to 1 and s is equal to 0. And this equation is known as Grubler equation. This equation is known as Grubler equation. Okay. And this equation became even more famous. This equation became more famous than the Kurzbach equation itself. This equation became more famous than the Kurzbach equation itself. That in many books nowadays, I've seen 3-4 books, right? In some of the books, they don't even mention the Kurzbach equation. Means this equation itself, they are saying it is a Grubler equation. This equation itself, the name of Kurzbach is slowly getting invalid, right? This equation, many books, because Grubler became so very famous with his equation, that the earlier equation, this equation itself, is also somewhere named as Grubler's equation. So why I'm telling you this? Because definitely there are possibility that you are asked to find out degree of freedom, right? And they might say to you, find the degree of freedom from Grubler's equation, find degree of freedom from Kurzbach equation. You should not get confused. There is only one equation from which you have to find out the degree of freedom, and this is this equation. There is only one equation from which you have to find out the degree of freedom, and this is this equation. Irrespective of what is mentioned in your question paper, they say you Grubler's equation, the Kurzbach equation, this is what you are going to. Okay. Okay. Now, I wish I had time to explain you this equation. This is such a fantastic equation. Why this equation gained the proper popularity, right? I wished I had a time to explain you that, but that won't be possible right now, right? So all of you, please try to do this equation fast. You have 1 minute in your hand. 1 minute. 1 minute. When 1 minute is too much, okay? Please be fast. We have lot to cover. जल्दी जल्दी ट्राई कीजिए. First, name the links. Okay. Let me tell you a few things. Always mark the fixed link as 1. All the fixed link will be 1. All the fixed link will be 1. ठीक है. अभी डिटेल में नहीं जाता why, how, who. ठीक है ना. Make sure all the first link, all the fixed link, you should mark it 1, and it will have one common number. You should not mark it 1, 2, 3 like that, right? All the fixed link will be numbered 1. After that, let me see how many links are there. So in total, I can see there are 10 links. L is equal to 10. Correct me if I'm wrong. Correct me if I'm wrong. First, we'll find out the degree of freedom. Okay, let me first find out ternary links. Here, the first person is the ternary links. How many ternary links are there? Guys, how many ternary links are there? How many ternary links can you find? What are ternary links? Links. It is not saying joints. It is not saying joints. Ternary links. How many ternary links are there? Ternary links are links which have 3 connection points. Very nice, right? Ternary links, you can see link number 8 and link number 7. 7 and 8 are ternary links. 7 and 8 are ternary links. So E option or E option to gaya. Option A and B. So elimination is always a very nice way to answer. Elimination is a very nice way to answer. Always try to eliminate your answers first, then try to mark the right answer. Your overall marks will increase. Okay. So if I talk about binary joint, ternary joint, can you give me? Okay, this is not part of the question, but definitely you'll have to use this. Let us see. First, let us see all the binary joint. Binary joint kitne hai? Kitne binary joint hai? How many binary joints are there? Let us see how many binary joints are there. This is the binary joint. This is the binary joint. This is the binary joint. This is a binary joint. This is a binary joint. This is a binary joint. This again is a binary joint. This is a binary joint. This is a binary joint. This is a binary joint. What about this joint? Is it a binary joint? Tell me. Yes or no? The last one. What kind of joint is that? Ternary joint. Very nice. Fantastic. So this is a ternary joint, and we know that one ternary joint is equal to 2 binary joint. We have studied in today's class itself. So this is equal to 2 binary joint. This is 2 binary joint. Right? So how many binary joints in total? Give me the number. How many binary joints in total? How many binary joints in total? Eleven, 12, right? There you can see 12 joints. There are 12 binary joints in total. Can you find any higher pair here? Can you find any higher pair here? No. So higher pair will be equal to 0. So what is the equation for degree of freedom? Degree of freedom is equal to 3 times L minus 1 minus 2J minus H. So what is degree of freedom? Come on, fast. 3 into 10 minus 1 minus 2 into 12 minus H. That is 0. So F is equal to 9 3 is 27, 27 minus 24, that is equal to 3. So what is the degree of freedom here? In this case, degree of freedom is equal to 3. Degree of freedom is equal to 3. So see, this is one of the tough question. I have addressed everything. We have been addressed what is binary joint. Okay. What is binary or ternary link? Here have been addressed degree of freedom. Okay. So this satisfies your concern. Okay. If you can solve this question, you're comfortable with this question, and I don't think you should have any problem. Okay. You should have any problem with degree of freedom questions, right? Now, let me give you a short note. Okay. If degree of freedom is equal to 0, then it is known as frame or structure. it will not have any motion. If degree of freedom is equal to 0, it will be known as frame or structure. If degree of freedom is smaller than 0, it will be known as superstructure. It will be known as superstructure. The strength of superstructure is more than that of structure. Strength of superstructure is more than that of structure. So if I'm saying it is a frame of structure, it will have no motion. No motion. It's just a frame. It is just a structure. There is no motion. Right? So generally, this kind of things are used for as you can say different. The part of civil engineering. Basically, it is part of structure. If I say structure, the part of civil engineering, right? So the frame, it can say it is a part of mechanical engineering, right? The frame, you can say it is a part of mechanical engineering. The frame of an automobile, the frame of an aeroplane, the frame of a helicopter, right? All these things have 0 degree of freedom, right? But if you say it is a structure, then it again becomes part of a civil engineering, right? So I hope your degree of freedom concept is clear. So a lot of questions hidden in this. Okay. So now we enter into simple mechanisms. Okay. What do I mean by simple mechanisms? Right. Now please mark this first line. The minimum number of links required to form a mechanism is 3 for cams and followers. So cams and followers will have 3 links. Minimum number of links is 3, and minimum degree of freedom. Sorry, minimum number of links to form a mechanism with only lower pairs is 4. Cams and follower will have one higher pair. ठीक है, बाद में ये देखेंगे cams and followers जब करेंगे, we'll just have a look at cams and followers, right? One higher pair. Right? One higher pair, right? So cams and followers, if you see minimum number of links there should be is 3. But if you talk about only lower pairs, with only lower pairs, then minimum number of links is 4. Right? So this 4 links mechanisms are known as planar mechanisms. This 4 link mechanisms, whatever you're going to have, this 4 link mechanisms are known as planar mechanisms. This is what our chapter is all about. Right? 4 link mechanisms are known as planar mechanisms because they are not going. They are 2 degree of freedom. Sorry, they are 2 dimensionals. 2 dimensionals. Right? The first one is 4-bar mechanism. Second one is single slider crank mechanism, and third is the double slider crank mechanism. Right? The planar mechanism, it consists of 3 classifications: 4-bar mechanisms, single slider crank mechanism, double slider crank mechanism. Okay, this is what we are going to study now. Okay, this is what we are going to see. Okay, now all of you, there is a term called inversion. This is again questions are being asked from inversion, and it's very important to know what are inversions before starting with the planar mechanisms. Right now, as we have discussed, a kinematic chain can be used as a mechanism only after one of its links is fixed. Right? A kinematic chain can be used as a mechanism only after one of its link is fixed. Without link being fixed, you'll not be able to use the mechanism. Now, in a 4-bar mechanism, as the name suggests, how many links will be there? There are 4 links. Please try to understand my point. In 4-bar mechanism, how many links will be there? 4 links. So which link to fix? Okay. The thing is, if you fix different links, you will obtain different mechanisms. If you fix different links, you may obtain different mechanisms, and these different mechanisms are called inversions. These mechanisms are called inversions to each other. Right? So, for example, there are 4 links. You can fix link 1 or link 2 or link 3 or link 4. If you fix link 1, you might obtain a different mechanism. If you fix link 2, you might obtain a different mechanism. If you fix link 3, you might obtain a different mechanism. If you fix link 4, you might obtain a different mechanism, right? Or it is also possible that 2 of the mechanisms which you have obtained by fixing different links are exactly the same. It might be possible. 2 or even 3 might be exactly the same, or even 4 might be exactly the same. Conditions might be there, right? So that is why if total number of links is L, so inversions will be less than equal to L. It could be equal to L, L भी हो सकता है, or it could be less than equal to L. It could be less than equal to L. Okay. For example, in 4-bar mechanisms, the number of links is 4, but inversions obtained is 3. There are 3 inversions. Double crank, double rocker, and crank rocker. In single slider crank mechanism, there are 4 inversions. Right? By fixing 4 different links, you'll have 4 different inversions. Right? 4 different mechanisms. Right? Similarly, in double slider crank mechanism, you'll again have 3 inversions. You'll have 3 inversions. Right? That is also something we'll have to see. We are going to see in today's lecture. Okay. So let us start with 4-bar mechanisms. Let us start with 4-bar mechanism. We have already seen this 4-bar, right? So it consists of 4 bars and 4 turning pairs. So this is also important. Sometimes they ask you how many turning pairs are there in a 4-bar mechanism. Very simple question, but you should know. If only one who have seen it, they will be able to understand, right? So what are the turning pairs? These are the turning pairs. You can see these are the turning pairs. 4 turning pairs. 4 turning pairs. So basically there are 4 bars and 4 turning pairs. Basically there are 4 bars and 4 turning pairs, right? So it can have 3 inversions. It can have 3 inversions. How? Dekhte hain. Right? That is what we are going to see. That is what we are going to see. It can have 3 inversions. Now you can fix this link, or you can fix this link, or you can fix this link, or you can fix this link, right? So it is up to you which link you are fixing, right, to use it, right? So you might obtain a double slider. You can obtain a not double slider, double crank. ठीक है, double slider नहीं आएगा. Double slider will not come. The double crank mechanism. You can obtain a double crank mechanism, or you can obtain a crank rocker mechanism, or you can obtain a double rocker mechanism. So what does it mean? What does a crank or rocker mean? Crank means when a link is capable of making complete rotation. When a link is capable of making complete rotation, it is called crank. When a link is capable of making only partial rotation, it is called rocker. It is called rocker. For example, let me say, for example, again, I'm assuming, let me fix this link, and after fixing this link, let me say this link, this pink one, it can make full rotation. It can make full rotation. So this will be termed as crank. This will be termed as crank. The input link. Let me say this is the input link. The input link can make full rotation, then this link is nothing else but crank, right? And let me say the output link, this is the output link. Output link cannot make full rotation, but it can only make partial rotation. Means you can go from this point to this point. This is the range. You can say this link, sorry, this output link, it can go from OA to OB and then return back to OA and then go to OB. So what is happening? Output link is making a oscillatory motion. OA to OB, OB to OA, OA to OB, OB to OA. So what kind of motion is this? This is partial rotation. This is partial rotation. Partial rotation. So if it is partial rotation, it will be called rocker. If it is partial rotation, it will be called rocker. If it is partial rotation, it will be called rocker. So this mechanism is called crank rocker mechanism. This mechanism is called crank rocker mechanism. Right? If both the links are crank, it will be known as double crank. If both the links, input and output links are rocker, it will be known as double rocker. Okay. Now there is a very important law that is known as Brasov's law. Very important law that is known as Brasov's law. For continuous relative motion between the links of a 4-bar mechanism, the summation of the length of the shortest and largest link should not be greater than the summation of the lengths of the other two links. ठीक है, इसको समझा देता हूं मैं आपको. ठीक है, I'll again quickly go through. ठीक है, for continuous relative motion, what does it mean? Let us not go very deep. I'll simply give you the final expression. What does it mean? Continuous relative motion means at least one crank. At least one crank should be there in the mechanism. If I'm saying continuous relative motion, it means there should be at least one crank, at least one. If there are two, I don't have any problem. But at least there should be one crank in the 4-bar mechanism, right? So to obtain at least one crank in the 4-bar mechanism, right, the summation of the length of the shortest and the largest link should not be greater than the summation of the other two links. The summation of the length of the shortest and the largest link should not be greater than the summation of the other two links, right? For example, in a 4-bar mechanism, there will be shortest link, there will be largest link, shortest link, largest link, right? And other two links, where S is the length of the shortest link, L is the length of the largest link, and P and Q are the other two links, right? So according to Brasov's law, if you want at least one crank, this law has to be satisfied. There is sum of the lengths of the shortest and the largest link should be smaller than equal to the length of the other two links. Right? So देखते हैं, is it, if Brasov law is satisfied, is it that you will always get at least one crank? No, it is not so. No, it is not so. Right? If Brasov's law is satisfied, will you always get one crank? No. But if you want one crank, Brasov's law has to be satisfied. Right? If you want at least one crank, this law has to be satisfied. Otherwise, you will not get it. But vice versa is not true, that if Brasov's law is satisfied, always you will get one crank. No, always it's not necessary, right? You might get one crank, you might get two cranks, you might get double rocker, right? But if you want at least one crank, or if you want two cranks, right, your Brasov's law should be satisfied. देखते हैं. Suppose Brasov's law is satisfied, and let me say smallest plus largest is smaller than P plus Q, right? So in what case we are going to get a double crank? In what case we are going to get a crank rocker? And what case we are going to get a double rocker mechanism, right? That is what we want to see. Now, if the smallest link is fixed, is something important. It can be oriented anyway. Okay? It can be oriented anyway. Now, if the smallest link is fixed, what you're going to get a double crank. If you're fixing the smallest link, which link you're fixing? You're fixing the smallest link. What you're going to get is a double crank mechanism. You're going to get a double crank mechanism, right? Now, if you're fixing the link which is adjacent to the small, it means that this is the small. Now, you're fixing a link. Okay, which is adjacent to the smaller. Now, the smallest link will always make a crank, and this will be the rocker. This will be the crank. This will be the rocker. बहुत ज़्यादा combination नहीं possible है. So here you'll obtain a crank rocker. Here you'll obtain a crank rocker. And now if the smallest link, is opposite to the fixed link, let me say this is the smallest link. This is, say, it could be the largest, it could be the PQ, whatever it is. Okay, I'm not concerned about that, right? But the smallest link is opposite to the fixed link. Okay, so the link opposite to the fixed link is known as coupler. Link opposite to the fixed link is known as coupler. So in this case, what we are going to get is a double rocker. In this case, you're going to double rocker. This will also be a rocker. Input link will also be a rocker, and output link will also be a rocker. So please remember, all of you, please remember, if the smallest link is fixed, you're going to get a double. Input is a crank, output is a crank. If the smallest link is adjacent, placed adjacent to the fixed link. If the smallest link is placed adjacent to the fixed link, what you're going to get is a crank rocker. The smallest link will be crank, the other link will be a rocker. And if the smallest link is placed opposite to the fixed link, if the smallest link is placed opposite to the fixed link, if the smallest link is placed opposite to the fixed link, now the link opposite to the fixed link is also known as coupler. The link opposite to the fixed link is also known as coupler. We obtained a double rocker mechanism. What you obtain is a double rocker mechanism. I know people do have confusion how to remember all these things, but if you give, yes, third is not satisfied. No, we'll not say not satisfied, it is satisfied, right? Law is satisfied. Law is satisfied. As I said you, if law is satisfied, it is not necessary that every time you'll get a double crank. You might also get a double rocker. But if you want a double crank, then the law has to be satisfied. Both the lines have different meanings. At least one crank. If you want at least one crank, if you want double crank or crank rocker, if you want double crank or crank rocker, the law has to be satisfied. If the law is not satisfied, you'll never have crank. If the law is not satisfied, you'll never have crank. If law is satisfied, yes, you can have crank, double crank or crank rocker. But it is not necessary that every time you'll have a crank rocker. There might be some other configuration like this. Whenever the smallest link is opposite to the fixed link, you'll have a double rocker. Okay, both the lines have separate meaning. If I'm saying if you want at least one crank, the law needs to be satisfied. On the other hand, the second line I'm saying is, if law is satisfied, you might get crank or you might not get crank. For example, suppose you are preparing for IIT, right? For example, you're preparing for IIT, or let me say you're preparing for this HL exam. You're preparing for HL exam. It is something like this. To enter into HL, you have to definitely clear the exam. Without clearing the exam, you will not be able to enter into HL. Right? Similarly, if you want double crank or crank rocker, if you want at least one crank, this law has to be satisfied. But if you clear the HL exam, because there will also be interview stage, right? If you clear the HL exam, it is not necessary that you will definitely get inducted into HL. To get into HL, definitely you have to clear the exam. But even if you clear the exam, it is not 100% that you will definitely get into each chair. You might be get rejected interview. Similarly, to get a crank or crank rocker, at least one crank, this law needs to be satisfied. But satisfying the law does not mean that every time you will get a crank. There are other possibilities also. You can also get double rocker. But if you want crank, this law has to be satisfied. If this law is not satisfied, if you are unable to clear the HCL exam, if this law is not satisfied, you can never obtain a crank mechanism. You can never obtain a crank mechanism. Like if you cannot clear the HCL exam, right, you'll never be able to get into HCL. This is what. Okay. Smallest plus largest, the second case is smallest plus largest is equal to P plus Q. Okay. What was this? This was smallest plus largest is smaller than P plus Q. This smallest plus largest is equal to P plus Q, right? So in this case, again, there will be two cases. Okay, there are two cases. The links arrangement will be something like this. It could be something like this, right? All the links are different size, 2, 5, 3, 4. So this is similar to case 1. Whatever you have done in case 1, you will get similar to that. Okay, if all the links are of unequal length, like link smallest is 2, largest is 5, and P and Q are 3, 4, right? Then all the conditions will be like case 1. Now, there's another possibility. What is the other possibility? Other possibility is something like this. Links are something like this. 2, 4, 2 plus 4, 2 plus 4. Right? In this case, you are going to obtain a parallelogram linkage. You can have a parallelogram linkage or a deltoid linkage. When parallelogram linkage, if equal links are opposite to each other. Equal links are opposite to each other. What is deltoid linkage? Equal links are adjacent to each other. Equal links are adjacent to each other. Okay, equal links are opposite to each other, equal links are adjacent to each other. So equal links are opposite to each other. What kind of link you are going to get is a parallelogram linkage. What are we going to get is a parallelogram linkage. Like it is also known as golden linkage. Why golden? Because either you fix the large one or you fix the small one. Either you fix the large one or you fix the small one. It doesn't matter. What you're going to obtain is a double crank. What you're going to obtain is a double crank. So that is why it is known as golden linkage. That is why what you are going to get is a golden linkage. The second option is the deltoid linkage. Deltoid, right? So in deltoid linkage, right? So if you fix the small, you'll get a double crank. If you fix the large, you'll get a crank rocker. If you fix the small, you'll get a double crank. If you fix the large, you'll get a crank rocker, right? If the law is not satisfied, you're always going to get a double rocker. Always. You always get a double rocker. If the law is not satisfied, if smallest plus largest greater than P plus Q, you'll always get a double rocker. Now give me the answer of this question. ठीक है, जल्दी जल्दी करो. गेट का आया हुआ क्वेश्चन है. Do it fast. Very nice. The smallest is the largest, P, Q. You can see smallest is adjacent to fixed implies crank rocker. So at least one link, that is the smallest link, you'll have rotation. Partial rotation, right? So what is the answer? Answer is 1. Right, so you'll have a crank rocker mechanism. Here you'll have a crank rocker mechanism. So the crank will have full rotation and the rocker will have partial rotation, right? So in this case you're going to have one link which is going to fully rotate, right? So this kind of question will be asked, and theoretically, direct theoretically question will be asked: parallelogram linkage, deltoid linkage, golden linkage, right? So when you're going to obtain double crank, when you're going to obtain a crank rocker, when you are going to obtain a double rocker, right? What is Brasov's law? Okay, lot many questions can be framed from here. Lot many questions can be framed. They are framed. Even this is a very good favorite topic of GATE, right? I think 6-7 times GATE has asked on Brasov's law, right? And good questions can be formed from this topic, right? Okay, so this was our 4-bar mechanism. This is our 4-bar mechanism. Now we enter into the next part, that is single slider crank mechanism. What you're getting into is single slider crank mechanism. ठीक है, I'll simplify this for you. ठीक है, एक बार simplify कर देता हूँ मैं. So there is one cylinder. It's not necessary that the cylinder is fixed. ठीक है, cylinder fixed होगा ये जरूरी नहीं है. It is not necessary that the cylinder is fixed. There is one cylinder for sure. Okay, so there will be one piston inside the cylinder. Okay, there will be one piston inside the cylinder. There will be one piston inside the cylinder. Okay, and then you will have a connecting rod. And you will have a crank. And you'll have a crank. Right, so मैं इस फिगर को नहीं एक्सप्लेन कर रहा, I'm not getting into this figure, ठीक है? So because it will again take another say 10 minutes to explain all these things, but ठीक है. So the cylinder is considered as the link 1. Cylinder is considered as link 1. Cylinder is considered as link 1. Okay, then the crank is considered as link 2. Crank is considered as link 2. Then you have connecting rod, which is considered as link 3. And then you have the piston, which is considered as the link 4. Piston, which is considered as link 4. So this is how the single slider crank mechanism looks like. So what we have done, in place of one of the bar, we have replaced it with the slider. So there is one slider, single slider, and crank. What is the meaning of crank? Now you all of you know the crank is going to make full rotation. What is the crank going to do? What is the crank going to do? The crank is going to do full rotation. Yes, right? The crank is going to do full rotation, right? So this is basically a single slider. Slider, which is the slider? Piston is the slider. Piston is the slider. Piston is the slider, right? So this is the single slider crank mechanism. Now I can obtain different. This is a single slider crank mechanism, right? I can obtain different mechanisms by fixing different links. So this is basically the kinematic chain. What I have right now is the kinematic chain. What I have right now is the kinematic chain. I can fix different links. For example, I can fix the crank, or I can fix the connecting rod. I'll have different mechanisms. I can fix the cylinder. I'll have different mechanism, right? Or I can fix the piston, and I'll have different mechanism, right? So all these different mechanisms are called inversions to each other. So how many inversions are possible here? How many inversions are possible? There are 4 inversions. There are 4 inversions, right? You fix the crank, or you fix the connecting rod, you fix the piston, or you fix the cylinder, right? So this 4 inversions, this mechanism, this means 4 different mechanisms we can obtain. We can obtain 4 different mechanisms. So when these mechanisms are put to use, okay, when these mechanisms are put to use, we'll get different machines. For example, cylinder fix. This inversion number 1. Inversion 1. Inversion 1. So you have one mechanism. When you put this mechanism to use, you can obtain 2 types of machines, either reciprocating engine or reciprocating compressor. For example, this is the most simplest example. Okay, all of us know about this. So this is the cylinder, and inside the cylinder you have the piston, and on the piston there is a connecting rod, and on the connecting rod there is the crank, right? So here what I have done is I have fixed the cylinder. So this is our first inversion. This is our first inversion. I fix the cylinder, right? So now you will have one input link and you'll have one output link. You'll have one input link and you'll have one output link. Now, if the input is the cylinder, is the piston, if you're giving input to the piston and taking out from the crank, this is nothing else but your IC engine. This is nothing else but your IC engine. Right? This is nothing else but your IC engine. If the input is this piston, means rotation, means combustion is happening. Because of the combustion there is pressure on what? Pressure on the piston. So the piston is moving forward. Because of the motion of the piston, the connecting rod will move. The connecting rod is moving, means the crank is moving, right? Now crank, this is the engine. Now the crank is connected to the transmission system, so the wheels will rotate, right? So what is happening? If the input is from the piston and the output is taken from the crank, you call it as a IC engine. On the other hand, if input is the crank and the output is the piston, what we call it as a compressor, reciprocating compressor. Reciprocating compressor, right? We use the electric motor. We'll use the electric motor and we'll rotate the crank. And what the piston will do? Piston will compress the air. Then again it will deliver. It will suck in air, suction of air, then compress the air, then it will deliver the air, right? So that is nothing else but a reciprocating compression, right? So this is the basic understanding I have given you. I'll not be able to explain each and every one for you. Okay, each and every one for you, each and every point, right? But why I have told you this? Because you should have an understanding what is an inversion. So this is inversion 1. You have inversion 2. Inversion number 2, right? Then if you fix the connecting rod, this is inversion 3. Then you can fix the slider, right? You'll have inversion 4. and left inversion 4. So how many? One question is being asked, how many inversions are there in single slider crank mechanism? There are 4 inversions. So if you put first inversion to use, inversion is nothing else than mechanism, right? If your first mechanism is put to use, you can obtain 2 different types of machines: reciprocating engine or reciprocating compression. Similarly, if you put your second inversion to use, second inversion means the crank is fixed, you can have Whitworth quick return motion mechanism or rotary IC engine, that is Xenom engine. Right? Whitworth quick return motion mechanism is used in this quick return motion mechanism, QRMM. QRMM, where it is used in shaper, planer, slaughter machines, in machine cutting, in machine cutting, right? Machine cutting, machine tools, metal cutting, sorry, not machine cutting, metal cutting and machine tools, right? So you have heard about the slaughter, scraper and planer machines, right? So in the forward stroke, it cuts the material, the return stroke, it comes empty. The forward stroke, it cuts the material, the return stroke, it comes empty, right? So here we have a kind of mechanism, right, where while cutting stroke, that is the forward stroke, it does it properly, slowly, right? While return stroke, because it is coming empty, it is not performing any work, so it is coming quickly, coming back quickly. That is why return quick return motion mechanism, right? Always remember, quick return motion mechanism is used in shaper, slaughter and planer, right? And there is one more quick return motion mechanism, that is when you fix the connecting rod, that is known as crank and slotted lever. This is Whitworth. The first one is Whitworth, then we have crank and slotted lever. So second one is more popular, more used. Second one is more used. Okay, we'll not go into the construction, it will take a hell lot of time. Okay, now again, crank fixed, you have rotary IC engine. This is rotary IC engine is generally used in rockets. Earlier it was used in rockets and big aeroplanes, right? So I'll simply write it as rockets, aeroplanes. Earlier aeroplanes were made up of rotary IC engine. Nowadays you have jet machine, right? The aeroplanes generally have jet, right? But earlier the aeroplanes had rotary IC engines, right? Then you have oscillating cylinder engine, not much into use, nowadays. The slider, if the slider is fixed, what you're going to have is hand pump or pendulum pump or bull engine. Hand pump, pendulum pump or bull engine, right? So this three are, better to say all. Okay, this is a very important slide. Okay, a lot of questions are being asked from this slide. Okay, please refer this slide before going. Okay, very good chances of you getting questions from here. Get very good chances of you getting questions from here. Okay, any questions you need to ask? We'll not go into the diagrams, each and everything, right? It will take 1 hour of time. But it is full of questions. How many inversions are there for single slider crank mechanism? Question might be like this also, right? In single slider crank mechanism, how many turning pairs are there? Tell me. How many turning pairs are there in single slider crank mechanism? Can you see how many turning pairs are there? 3 turning pairs. What are the 3 turning pairs? Let us see. There are 3 turning pairs. There is 1 turning pair here, 1 turning pair here, and 1 turning pair here. Right? So how many turning pairs are there? There are 3 turning pairs. And you can also see there is one sliding pair, right? There are three turning pairs and one sliding pair. So this kind of question, simple observation based question. Okay? Then you have how many inversions are there in single slider crank mechanism? Question will be there like this. Rotary IC engine is obtained when which of the following is fixed? You might be given cylinder fixed, crank fixed, connecting rod fixed, or slider fixed. Then the question might be formed, if slider of a double single slider crank mechanism is fixed, which of the following machines or mechanisms will be obtained? Reciprocating engine, Whitworth quick return motion mechanism, oscillating cylinder mechanism, or it can be given bull engine. Right? So this kind of combination of questions can be formed, right? Which of the following, which the Saper machine uses which of the following mechanisms, right? You might be given four options. So all different combination of questions can be asked. So please revise this very carefully. Shall we move forward? Now you have double slider crank mechanism. Double slider crank mechanism. Now the next is double slider crank mechanism. Right. So initially you have seen the first one is a single slider. Sorry, first one you have seen is the 4-bar mechanism. Then you have seen single slider crank mechanism. Now what you are going to see is the double slider crank mechanism. Now what you are going to see is the double slider crank mechanism. So what is a double slider crank mechanism, right? What is double slider crank mechanism? You can see here, right? There are double sliders. Two sliders are there. One slider, this is the second slider. There are two sliders, one slider and the second slider, right? That is why it is known as double slider, right? So how many turning pairs and how many sliding pairs are there? Can you see it properly? How many turning pairs and how many sliding pairs? Can you make it out? Can you make it out? How many turning pairs and how many sliding pairs? Can you make it out? Bolo, how many sliding pairs? So how many? What are the different members? Let me say these are the links. Let us first mark the links. This is link number 1. This is, this is link 2. This is link 3, and this is link 4. There are 4 links, right? So this one you can say this is the slotted plate. This slider. There are 2 sliders, and this is nothing else but a connecting rod. Connecting rod. So now you can fix the slotted plate, right? You can fix one of the sliders or you can fix the connecting rod. So you can clearly see how many inversions are there. There are 3 inversions. Because you fix this slider or you fix this slider, you're going to have the same mechanism. Right? You fix slider number 1 or slider number 2, the link 2 or link 3, you are going to have the same mechanism. So there are only 3 inversions possible. You fix the slotted plate, you'll get a mechanism. You fix the connecting rod, you'll get a mechanism. You fix one of the sliders, you'll get a mechanism. Right? There are 3 inversions. Okay. So how many turning pair, as you said? There are 2 turning pairs, right? You can see this is one turning pair, this is one turning pair. Right? Turning pair. 2 turning pairs. What else? Are there sliding pairs? Here are 2 sliding pairs. You can see, right? This is one sliding pair. This is one sliding pair. The sliders will slide. 2 sliding pairs. There are two sliding pairs, two turning pairs, two sliding pairs. Okay. So how many inversions are there? There are three inversions possible. So let us go through the inversions. This is very important. Zyada kuch nahi. You just need to remember the inversions. You just need to remember the inversions. What are the different inversions? Right? Now first, if the slotted plate is fixed, you will get an elliptical tremor. If the slotted plate is fixed, you will get a electrical tremor. What does the electrical tremor means? Electrical tremor means this sliders will keep on moving, right? When this slider will come down, when this slider will reach here, 1, let me say this is 1, and let me say this is 2. When 1 reaches there, the 2 will be somewhere here. Right? Then when 1 will reach here, 2 will be somewhere here. Right? Then again this will go on happening. Again 1 will reach here, 1 will again reach back here, 2 will be this time the other side of the rod, slotted bar, and this will keep on happening. This will keep on happening, right? So the 1 will keep on moving in the vertical plane, right? And the 2 will be moving, keep on moving in the horizontal plane. This will keep on happening, right? So when this is happening, the locus of all the points on the rod, connecting rod, right? All the points on the connecting bar as a locus of the ellipse, except the midpoint and the end point. Except the midpoint and the end point. The midpoint has a locus of circle and the endpoints have locus of straight line. So which one is the connecting rod? Which one is the connecting rod we are talking about? The connecting rod we are talking about is this. This is the connecting rod. So all the points in the connecting rod, all the points in the connecting rod, all the points in the connecting rod will have, okay, ellipse. Will trace an ellipse. Connecting rod or connecting bar. Okay, इसका equations भी बना सकते हैं, ठीक है? Let us not go into all those things. Now, next is one slider is fixed. One of the slider is fixed. Now, if one of the slider is fixed, okay, let me say this slider is fixed. Now, this slider is not going to move. This slider is not going to move. So, I am just cutting this off. So, I'm fixing this slider. Only the slider number 1 will keep on moving. It will move up and down. It will move up and down. So, you should be able to imagine what exactly is happening. Okay, when a slider moves down, let me say, it comes down a little bit. Okay, when it comes down, now this rod is, the length of this rod is fixed. So when the slider comes down, the rod will become something like this. Slider will be something like this, and the slotted plate would have moved a little bit forward. Right, the slotted plate would move little bit forward. Are you able to visualize this? When the slider will move on the slotted plate, because the length of the connecting rod is fixed, right? The slotted plate will move little bit forward, right? So this way what is going to happen is, the slotted plate will keep moving to and fro. The slotted plate will keep moving to and fro. To and fro motion. To and fro motion of the slotted plate. To and fro motion of the slotted plate, right? So this mechanism is known as Scotch-Yoke mechanism, right? What is an application of Scotch-Yoke mechanism, right? It is used in power hacksaw. It is used in power hex. So just imagine what is going to happen if you are installing cutters here. If you're installing cutters here, right? So the slotted plate, the extruded portion will keep on moving up and down. Up and down means to and fro. It will move forward, it will come backward, it will move forward, it will come backward, it will move forward, it will come backward, right? So what exactly is happening? What exactly will happen if you attach a cutter there, right? It will act as a power hacksaw. It will act as a power hacksaw. So what is happening? We are installing a motor here. What will happen? We will simply install a motor here. We'll install a motor here. We'll install a motor here. The motor will run the crank. The crank will make full rotation, and because of the full rotation, it is converted into to and fro motion. It is converted into to and fro motion, and we have attached a cutter, so it will cut the, it will act as a, okay, I'll add you. No trouble, no trouble. I mean, I'll add you. You can go out and you can come in. I hope you can see me now. See the screen. Okay, fantastic, fantastic, right? So the last slide for today's class is if you fix one of the sliders. Okay? If you fix one of the sliders, what we are going to get is a Oldham coupling. If you fix one of the sliders, we are going to get a Oldham coupling. Okay? I could have shown videos for it because generally I show it in gate class, but we'll not have the enough time for that, right? So in Oldham's coupling, okay, if you take Oldham coupling, right? Two questions can be asked, 2 to 3 questions can be asked. Okay? First of all, when do you obtain the Oldham coupling? In a double slider crank mechanism, if you fix this slider, you get an Oldham coupling. So when do you use Oldham coupling? Oldham coupling is used to transmit power between two shafts having lateral misalignment. What is lateral misalignment? This is lateral misalignment. This is one shaft. This is one of the shaft. Right? And this is one more shaft. This is another shaft. So these two shafts have lateral misalignment. So what you can do is you can connect it using Oldham coupling. Okay, this is the kind of coupling which is called as Oldham coupling, right? So here one of the slider is fixed, right? You can connect shafts having lateral misalignment using Oldham coupling, right? One more question I'll give you. Okay, there are 2 questions here. Slider fixed Oldham coupling. Oldham coupling is used for connecting shafts in lateral misalignment, right? And what kind of stress the shafts will obtain? Because it is rotation, there will be only twisting moment. Okay, there will be only twisting moment. This was a question asked in one of the engineering service paper, right? What kind of stress will be there in the shafts in the of the in Oldham coupling? Because of rotation is there. Rotation means twisting moment, right? Okay. So there are 2 types of misalignment. One is angular misalignment. Angular misalignment. Angular misalignment is something like this. Once after this one, this is one shaft, and this is the other shaft. This is the other shaft. Right. So if you have angular misalignment, what link you use? We use Hooke's joint. Hooke's joint. It is also known as universal coupling. Right? It is also asked. Okay, this is not part of theorem machines. It is a part of theorem machines, but not generally not being frequently asked. Okay, so Hooke's joints, universal coupling. It is for angular misalignment, and for lateral misalignment. This is lateral misalignment, as you can see. This one soft, this one soft. Okay, this soft one, this soft two. We use Oldham coupling. Okay, what is Oldham coupling? If the slider of the double slider crank mechanism is fixed, you get an Oldham coupling. Right? Thank you. So we were able to complete in exactly 2 hours of time. We were able to complete this in exactly 2 hours of time. So I hope it was useful. Were you able to understand each and everything? I know it was very fast. Generally, this class is taken in 5 hours. Okay? We take 5 to even sometimes if the batch size. Oh, yes, I can understand. I can understand. Right? I can understand. You did get lot of data, but it was all of them were important with respect to objective. There is no other option. I have tried to skip as much as possible, right? I have tried to skip as much as possible, but all of them is very important with respect to objective point of view, right? And theory of machines is basically, you can see a lot of this kind of questions can come from theory of machines, right? It is unlike machine design. Machine design is morely numerical in nature. You will not have many one-liner objective questions from machine design, right? But from theory of machines, yes, lot many concepts, lot of things to understand. तो ठीक है, देखते हैं. First class down, 4 more to go, and yes, it is going to be not going to be easy, right? Theory of machines is not going to be as simple as that of machine design. Okay, thank you. Do revise properly. Ask me whatever doubts you have. Right? You have my number. You have me in your WhatsApp group. Right? You can ping me. Right? Whenever you want, and we are always there to support you for your exam. We are always there to support you for your exam. Okay. Take care. Good night. Good night. I'll end the meeting. Right? If you have any doubt, you can ask me over WhatsApp. Thank you. Thank you. Thank you. Good night.